So how are you all doing today? It's Friday. It is Friday. I am happy about that. Any questions on you guys' mind before we get started today? All right. Well, let's finish up chapter 8 and get on to our Friday then. Main goal for today is looking at the last couple rotational concepts and closing out chapter 8. So that means that next week we'll do chapter 9, which will be a short chapter on pressure and buoyancy. I intend for it to be, I intend for chapter 9 to be well concluded during next week so that we can move into test prep for the week after. So, when we get to test 2 in just under 2 weeks now, depending on when you take it, it'll be on chapters 6 through 9 and end of next week and also during class the week of the test. We'll review everything and I'll post another practice test for it like I did the first one. For right now though, before all of that, we have to finish chapter 8. So any questions or concerns before we get on with that? All right. On Wednesday, we started talking about moment of inertia, which is the angular counterpart to mass. The notion of angular momentum. I keep saying the wrong word today. Excuse me if I stumble over my words once or twice. The notion of moment of inertia says that matter wants to rotate to different degrees depending not only on the mass of the object, but also its shape and what axis you are spinning it through. It's the I in all of these formulas, and you calculate an object's moment of inertia using this chart in your notes and on your formula sheet, back page. Every different object just has a slightly different formula. They're all basically mass times radius squared, but they have a different weird fraction on the front just depending on the shape. You don't have to memorize them. You can just check this table for the weird fraction on the front. And at any given time where you need to consult this table, I will make sure you know what shape something is so that you don't have to guess. Now, we brought up moment of inertia because we were talking about torque. Torque is the counterpart to force. The force equation has mass in it, so therefore so too does its angular counterpart. And there's 2 more formulas that have moment of inertia in them that we're going to talk about today because they are the angular counterparts of concepts that also have normal mass in them. Linear momentum, rho equals mass times velocity. Its counterpart is angular momentum. I don't know why it's L, unfortunately. Angular momentum equals moment of inertia times angular velocity. And then, if you recall, linear kinetic energy was 1/2 times mass times velocity squared. Its counterpart is angular kinetic energy, which is KE with the theta subscript. And that's 1/2 times moment of inertia times angular velocity squared. Wherever you normally see m's, you now have i's instead. So those are the last 2 things we're going to look at today. Angular momentum and angular kinetic energy. And that'll round out every possible thing related to spinning that we're going to be doing in this class. So if you're sick of rotation, the end is in sight.
Got the spins. Got the spins.
Got the spins. I'm about to have the spins because I have a couple demonstrations I'm going to do later this class that involve me spinning. I will get very dizzy, and I hope that it drives the point. So stay tuned for that, I guess. Now, contrary to how they're written on this slide, I actually want to look at kinetic energy first. So first up, angular kinetic energy. because all forms of motion require energy, whether that form of motion is linear or not. Linear velocity requires something to have linear kinetic energy. Subatomic motion requires energy too, because if an atom is moving, it's because it has thermal energy. So every single form of motion requires energy, and that includes spinning. You can look at something and see that it is moving, but if it doesn't have a linear velocity, you can't use the normal kinetic energy formula to figure out how much energy it has. This thing doesn't, like, what's its linear speed right now? 0, because it's staying in my hand even as it spins. But you can see it moving. You can tell it has energy. And I even had to do work to get it spinning in the first place, because I have to physically exert force on it while my hand is moving some distance. So I do work, I give up energy, the wheel moves, the wheel now has that energy, and this is just the form that it needs in order to spin. So if something is actively spinning, it must have this form of kinetic energy. And it is still kinetic energy, it's just diverted to a slightly different purpose. Conceptually, how does this notion feel? All right, so spinning takes energy. This creates kind of an interesting scenario for a rolling object. Because if something rolls, like say a sphere down a ramp, it's going to have both linear and angular kinetic energy at the same time. Because it would need both to be linearly moving and also spinning simultaneously. So objects can possess both types at once. If you have linear speed, if you have linear kinetic energy and no angular kinetic energy, then you're just going to be moving forward without rolling. Likely you're sliding. If you have angular kinetic energy and no linear kinetic energy, you'll just be spinning in place. But if you have both, you can roll, moving forwards and spinning at the same time. And for a rolling object, you must have both at once. To roll, both linear and angular kinetic energy must be present. And that's what we're going to look at in the context of this sphere. We're going to place this sphere at the top of this ramp, 2 meters above the ground. And we're going to think about this like we did back in chapter 5. That was the energy chapter. So, what form of energy does that sphere have motionless at the top of the ramp?
Potential.
What type of potential? Exactly. So, flashing back, total energy initial equals total energy final, because it's not destroyed, it just changes forms. Initially, we've got some amount of GPE. That's the only type that it has while it's just sitting there. And whether it's a sphere or not, that's all that's going on right there at the top. Whether it's a sphere or not, whether it rolls or slides, that's all that it has in this initial stage. What happens to that GPE as the sphere descends, rolls down the ramp? Turns into KE, because it's moving at this point. It needs KE in order to move. As its height decreases, its GPE decreases until you reach the ground and are at height 0. At that point, all of that energy is going to transform into kinetic energy, and so the sphere will roll away from the ramp at its top speed. Now, this is how we normally would treat a problem like this. We've done ones like this before, showing the energy transformation like this, correct? And this is the basic transformation of anything that is falling straight down or even just sliding down a frictionless surface. We've usually treated them as frictionless for simplicity's sake. And if there isn't any friction, this is the extent of it if it is sliding or falling. Sliding or falling in a frictionless world. However, the world usually isn't frictionless, and spheres tend to roll in a world with friction. Weirdly, if friction didn't exist, objects wouldn't really roll along the ground. Rolling and friction are kind of tied into each other. So in a frictionless world, this thing would just slide down the ramp without spinning. Weird thing to visualize. But in the real world that we live in, it's going to roll down the ramp, which means it will not only have linear kinetic energy, it will also have angular kinetic energy as a requirement. Because if it doesn't have this, it isn't spinning. And so if something rolls, it basically has to give up some of its linear kinetic energy to be able to be spinning while moving forward, in order to have both types at once. Because there's only a fixed amount of energy in the system. Left side doesn't care if you're sliding or rolling. There's only a fixed amount here, and if you're sliding in a frictionless world, it's all just going to become linear Ke. But if you are rolling, some of it has to go here instead. It's basically comparing 2 equals 2 to 2 equals 1 plus 1. Does that track? So when you're rolling, you have to sacrifice some of your linear kinetic energy in order to have angular kinetic energy and to be able to spin. Which means, theoretically, and this is purely theory because we don't really live in a world like this, theoretically, you should be moving faster if you slid down the ramp in a frictionless world than if you rolled down a ramp in a world with friction. And we're going to demonstrate that. We're going to figure out the linear speed of this sphere, both sliding without friction, but also while rolling. So, real quick, we're just going to pretend this thing doesn't roll. We're just going to pretend it is sliding in a frictionless world. Maybe it's just a box with the same mass. We're just going to pretend that's not there first. We're just going to look at it the old-fashioned way, determine what its speed would be sliding in a frictionless ramp, or as close to frictionless as we can get. So we're just going to treat it the old way to see what happens. GPE is mgh, Ke is 1/2 mv squared, height initial, velocity final. Sphere's mass is 1 kilogram, G is 9.8. The ramp height is initially 2 meters. 1/2 times 1 times unknown velocity squared. And again, treating this as if it wasn't spinning, it's just like a box sliding in a frictionless world. I believe this VF slide frictionless would be 6.26 meters per second. Does anyone's math agree or disagree with that? So that would be sliding, not rolling, down a frictionless ramp. And that's how we used to do this, right? I never really gave any examples where things were rolling. I would always say like falling straight down, ignore air resistance, sliding down a slope with snow, ignore, ground friction, things like that. None of those technically involved any rolling. Okay. So this is the old way we did it. Sound familiar? Just a flashback to chapter 5. All right. Now we're going to factor in the rolling. We're going to fully treat this as if it is rolling, spinning while moving down the ramp. And to do that, we have to factor in some of its energy has to become angular kinetic. So the way that we do that is we literally add that to the right side. On the final end of things, some energy has to turn into that form. And so I'm just going to modify what's on the board. You shouldn't like erase anything. I'm just showing the modification. You should write it a second time, but I only have so much board. What is the new formula for angular kinetic energy?
1/2 moment of inertia times the angular velocity squared.
Precisely. Now, if our goal is still to find VF, this is a slight problem because we don't know I and we don't know omega. So we need a workaround. We need other things to plug in for those numbers. We're kind of at a 1 equation, 3 unknowns scenario. So let's find 2 equations to plug in. What can we do with I?
Look at the chart.
Yeah, we know we're dealing with a sphere, so we can just look at the chart. Moment of inertia of a solid sphere, note hollow is technically different, interestingly. Solid sphere, 2/5 times mass times radius squared. Yes, that fraction feels kind of random. So instead of I, we're going to do 2/5 mass times radius squared. And thankfully we know the sphere's mass and radius. The other slide said mass was 1 kilogram and radius was 0.3 meters, I think. So we know those things. They aren't unknown anymore. That eliminates I as a problem. We do, however, still have omega squared. So we got to figure out something else to do with that. Omega is, again, angular velocity, so that tells you how fast it is spinning at the bottom. How can we compare that to the linear velocity? Is there some sort of connection there we can use?
Velocity equals radius times angular velocity.
Yep. You get this little column of formulas in the, between the angular and the linear ones. These exist to turn linear into angular and vice versa. So if we've got an omega in the formula, we can use this to instead turn it into a v, which is what we want. We want velocity, so let's use this to get rid of the thing we don't want and replace it with the thing we do. So if v equals r times omega, a little bit of algebra, divide by r, we get omega equals v over r, and that's what we'll write instead of omega. Note though, the omega is squared, so we'd have to square both parts of that fraction. So I'm going to go ahead and write in VF squared over R squared instead of omega squared. And that eliminates every unknown except VF. So we are back at being able to plug everything in and proceed. Any questions at this premise or setup so far? All right. Before moving forwards, I'm going to point out the r's are going to cancel because we've got 1r squared in the numerator and 1 in the denominator. So those will just go away, which is nice. Technically means that the size of the wheel doesn't really matter here, only its mass. Now that's only true for the linear speed that we're calculating. The radius does matter for angular speed, but not for linear. So, again, I'm just modifying what was up here. Our new term is going to simplify down to 1/2 times 2/5 is 1/5. mass is still 1 kilogram, the R's cancel out, and that just leaves behind another VF squared. Bless you. So I think that actually simplified pretty nice. It kind of now pretty strongly resembles the normal kinetic energy contribution, in my opinion. It also kind of gives us a ratio of the two, because the mass is the same and the VF is the same, so this just means that, well, the angular kinetic energy is about 2/5 the linear kinetic energy. Which actually might be where the 2/5 came from on the formula. But VF is still our only unknown, so we're good to try to find that. Left side should simplify down to 19.6. On the right side, we've got 1/2 times VF squared plus 1/5 times VF squared. Since they both have a VF squared in them, we can't add them normally, or you can use the distributive property, your method of choice. Either way, it should end up resembling 19.6 equals 0.7 times VF squared, or 7/10. And our final VF, when factoring in that the sphere is going to roll when in a world where friction exists, should be, correct me if I'm misremembering, 5.29 meters per second, which is about a whole meter per second slower than if this thing were to slide in a frictionless world. Get the wheel out of the way. So 2 things to note here. One, this is how you factor in angular kinetic energy into kind of a classic chapter 5 style energy transformation if an object happens to be spinning or rolling. And 2, I just find it kind of interesting to think that in a frictionless world, sliding is faster than rolling. Because the spinning part of the rolling leaches energy away that could just be in the linear form instead. Now, realistically, friction exists, which means this would never happen in real life unless you can get the surfaces involved as literally slick as possible. It is possible though. If you take a ramp and polish it and grease it up as much as you can, and you put a cylinder on it, it might actually start sliding before it starts rolling.
Is that why bowling balls sometimes slide down the lane rather than spin?
Exactly. If the friction is weak enough, it'll slide until the friction acts enough to get it rolling. Because weirdly, again, rolling is a function of friction. An object that is in a frictionless world, the wheel would just slide. But if friction is acting, that's a force pointing technically at a right angle to the radius, and therefore it's going to exert a slight amount of torque that will eventually cause rolling. And that's why sometimes the ball starts sliding and then picks up spin. That's a good example, thank you, I hadn't thought of that. So there are cases where, a round object will slide before it actually starts rolling. Those tend to be low friction environments like bowling, where both the field and also the balls tend to be very polished. Lane, excuse me. Realistically though, in the normal world, which isn't usually as polished and slick like a bowling alley, rolling is way more efficient than just sliding across the gravel. And it's why vehicles have wheels. If we wanted to factor in like a large amount of friction, like again trying to drag something across the parking lot, instead of factoring in angular kinetic energy, we would factor in the work done by friction, force of friction times the distance you slide. So a bunch of energy would go to that instead of linear instead. So in a world with friction, rolling is better than sliding. But in a frictionless world, sliding is better than rolling. So if friction didn't exist, we'd all just skate around on our shoes instead of walking or using wheels. It would still be kind of a pain though, because the only way to stop yourself would be to plow straight into, whatever you're moving towards. Like when you're at the skating rink, or at least when I was at the skating rink, in order to stop, I would just have to crash into that barrier separating me from the pizza. So, questions on the concept of angular kinetic energy? Alright, so, last rotational concept, and I'll make it brief before the weekend. Last one we'll talk about is angular momentum. Formula for that is, once again, L equals moment of inertia times angular velocity as a direct contrast to linear momentum being rho equals mass times linear velocity. So direct counterpart like all the others. If you recall, linear momentum is a measurement of how hard it is to stop an object that is moving. It's a measurement of how much that object wants to keep moving at the same speed in the same direction forever. And the more momentum it has, it is harder to make that change, the harder it is to stop the object in question. The same is true for linear momentum. The more something is spinning, the more it wants to keep spinning the exact same way in exactly the same direction. Wheels don't spontaneously just start rotating in the opposite direction, right? If you are moving very fast forward, throwing the car into reverse does not automatically cause you to start rolling backwards. You have to slow down first and then roll backwards, because the wheels all have angular momentum. They want to keep spinning forward. You have to force them to turn around. They want to keep spinning, same speed, same orientation. Bless you. That said, those similarities are there, but angular momentum is still kind of weird. And that's me saying that professionally as a physicist. Professionally speaking, angular momentum is weird for a few reasons. One, linear momentum is strictly a one-dimensional at a time thing. Even if you're moving on an angle, if an object's velocity points at a weird angle, it's still a one-dimensional line. It's just not in one of the normal planes. Normal linear momentum is straight line, one-dimensional only. But rotation is kind of inherently a two-dimensional activity. Because if something is spinning, it's rotating within an entire two-dimensional plane simultaneously. And I'll explain what I mean by that. When I spin this tire, parts of it are moving within the x-axis. Namely right up here, the instantaneous velocity of this part of the tire points this way, right? Kind of like when we were looking at the moon's velocity. The instantaneous velocity of this part of the tire points negative x, and this part of the tire, the very bottom, points positive x. So parts of this thing are moving in the x-axis, but parts of it are also moving in the y-axis. Namely, this section is pointing, its instantaneous velocity points negative y. This section's instantaneous velocity points positive y. So different parts of the tire are moving in different axes. So what we call this is the wheel is moving, rotating throughout an entire two-dimensional plane. 2D plane means, x times y, like the board behind us. The board is a flat 2D plane, x-axis times y-axis. The wheel is too, it's just, a distance away from the board, but it is still a flat plane. Does that make sense? It is flat, basically. So when the wheel spins, it's spinning throughout an entire plane. And unlike linear momentum, where something wants to keep moving in a straight line, the wheel wants to keep spinning in the exact same two-dimensional plane. It not only wants to spin in the same direction at the same speed, it wants to spin in the exact same orientation, the same two-dimensional plane that's already spinning in. Meaning that the wheel wants to stay like this and will not spontaneously rotate planes to do this. Because this is a different 2D plane. The axis is shifted. So if it's rotating like this, it's in this 2D plane, and it does not want for that plane to change at all. It doesn't want to spontaneously do this, or even this. It doesn't want to change at all. It wants the plane to stay totally in the same orientation. And so wheels that are spinning tend to stay spinning in the same orientation and will fight you if you try to change that. Do you recall possibly learning to ride a bike? You might have been given a tip to never do this with your handlebars. Sound familiar to any bike riders? When you do this, you are changing the plane of the tire. Normally the 2D plane is here, but when you turn the handlebars, the plane changes to here. Tire doesn't like that. And so doing this is a very quick way to be eating dirt. Sound familiar? I wiped out a few times doing this at first. Instead, the tip that was given to me is just to lean into your turn, because it's a more subtle change. The wheel doesn't fight back as hard. But it does still fight you. And actually, you can get a bike to roll forward by itself without a rider. If you physically take the bike and throw it forwards fast enough, once the wheels get spinning, they want to keep spinning in the same plane, and it'll just keep rolling without anyone on it. Because the wheels don't want to fall over. They only slow down, it only falls once it slows down and loses its momentum. Once the momentum is weak enough to not stay upright anymore. I will now demonstrate an extreme case of this. Note that if this wheel was not doing anything, left by itself, and I hang it from this rope, it sits here like this. It just hangs flat, not doing anything else. But if I spin it first, before doing that, and then I hang it from this rope, it doesn't want to fall over, so it won't. It's fighting gravity right now. It is resisting gravity's pull, trying to level it out, and it only falls once it slows down. Its own angular momentum says, no, stay in this plane until it peters out and loses the ability to fight back. This is a gyroscope. If you've ever heard the term gyroscopically stable, it means that whatever device is gyroscopically stable has something inside of it spinning like a top. And that top physically wants to keep spinning like this forever. And that's why, like a Segway, will stay upright even though it only has two wheels. The gyroscope inside is telling it, stay oriented like this. Same with some drones, I think, have gyroscopes in them. Make sure that the camera and everything is level even as it's turning and stuff. Same with just normal tops, if I'm being honest. If you just spin a normal top, it stays oriented correctly even if you flick it across the table. It might zap around a bit, but eventually, as long as it keeps spinning, it'll just right itself like a gyroscope. That's because angular momentum tells the thing, change nothing for as long as it's still spinning. If you try to change it, it'll fight you. To just kind of give another example, and if you want to try this out for yourself, you can grab the wheel at the end of the class. I don't even have to hang it from the rope. If I just try to move this thing around, it fights me. If you've ever, again, messed up on a bike and felt the tires wobbling, this is what's happening right now. It is fighting me and it is uncomfortable. And I can show again that it will exert force back on me to keep this from happening. What I'm about to do is I'm going to spin this thing while sitting on this stool, and And then I'm gonna turn it, and you'll see that it is working against me while that happens. All right. So, I did not kick off the ground. The wheel right now is causing me to rotate, because I tilted it and it's mad at me. I can even, yeah, there we go. The wheel is the only thing turning me around right now. My feet are not on the ground, and I'm not moving anything but my arms. Change it, and it fights you. So you can try that out yourself if you want. So that's what angular momentum says. If something is spinning, it wants to keep spinning exactly the same way and change nothing. Make sense so far? And again, it has a surprising amount of applications. But there's one other place you might have seen something like this. And for that, I'm going to turn your attention to this formula down here. This is the direct comparison to momentum initial equals momentum final. Linear momentum is conserved in a collision, and so too is angular momentum, because it's still momentum. Now, an angular collision is kind of weird to envision, because humans only really think of things colliding in straight lines, if I'm being honest. An angular collision really involves any sort of change in a given object's, angular velocity, or any given single object's angular momentum. Like, for example, an angular collision might resemble one gear spinning by itself at high speed, and then simultaneously another gear slams into it, and now they're both spinning together. This sort of thing happens in your car gearbox, by the way. The transmission. If it's spinning fast on its own, it has a certain amount of angular momentum. Slam in the second gear, now they're both spinning. They're sharing the initial total across the two, like how when two objects collide, some of the momentum from the first enters the second. So that's one type of angular collision, but there's another type too, the weird type, and it's the one I want to show you. Who's watched figure skating? All right. I was trying to remember when the next Winter Olympics are. Anyway, have you ever noticed how a skater might, say, start spinning in place on one skate, arms and legs out, kind of like this? And they're just spinning in place on the one blade. And while they're spinning, they might pull their limbs in and start speeding up, like going really fast in place, very dizzy looking. And then they'll throw their limbs back out, exit the turn, and go back to normal. That is technically an angular collision. When they enter the turn, when they're like this and spinning, their body has a certain amount of angular momentum. And the weird thing with moment of inertia is mass doesn't tend to change spontaneously. Like, the person's body doesn't suddenly have more or less atoms in it. That doesn't happen. And the same was true with linear collisions. Mass never really changed in those. We only really looked at velocity changing for like cars slamming into each other. But the weird thing about angular momentum is it doesn't just care about mass, it cares about the whole moment of inertia. And moment of inertia is not just a function of mass, it is also a function of radius. So mass might not spontaneously change, but size sometimes can. Namely, as it applies to figure skating, the person, when they pull their limbs in, they are changing the radius of their body. Normally they're like this, but now they're like this. The radius goes down, meaning that even if their mass doesn't change, their moment of inertia drops. And since their body has to have the same amount of angular momentum in it, so the total momentum is the same on both sides, if I gets smaller, omega has to increase to keep the same amount of momentum in their body. When they pull their limbs in, they decrease their radius, they decrease their moment of inertia, angular velocity increases to compensate. And this is what I'm physically about to do. I didn't describe it before, but this stool right here is on a rotating platform. It's got the best ball bearing in it out of all the stools in the room, so it's the best one to show what's about to happen. I am going to demonstrate what the figure skater does, except this way doesn't require ice or any figure skating talent. I'm going to sit on this stool, and like how the skater does, I'm going to have my arms fully extended. I'm holding these weights to amplify the effect. It's more subtle if you just have your limbs, so I'm just using this to make it more obvious. I'm increasing the mass distribution of my body. I'm going to hold these with my arms fully extended, and I'm going to spin myself in this stool. And I just want you to note what speed I'm moving at when I do that. And then once I'm in motion, I'm going to pull all my limbs in, decreasing my radius, decreasing moment of inertia, and you'll see what happens to my angular speed. Ready? All right, note my speed, and pull! Oh, geez. It's hard to do this in a stool without a back. Oh, dizzy already. Not a good sign. All right, and pull. And back out. And pull. And back out. Please tell me that was very obvious. I don't want to do it again. Room spinning. Help. Once more. Sometimes spinning in the opposite direction helps dizziness. Fun fact, I'm not a biologist, but I believe dizziness is also caused by angular momentum, as it turns out. Because if you're spinning, all your brain and ear fluid is also spinning, and when your skull stops, the fluid keeps spinning. Which is why spinning once or twice in the opposite direction helps get rid of it. So, weird applications of angular momentum. Again, this works because moment of inertia can change, whereas mass tends not to change by itself. Questions? Make sense? I hope. All right. Very last thing we'll do today is just put numbers to what I just did. This isn't going to be a perfect calculation because humans are not a standard geometric shape. There's not like a formula for, moment of inertia of this. So we're just going to assume I'm a cylinder and just deal with the fact that's not totally accurate. Let's say human of mass 95 kilograms holding two 10-kilogram weights. That means the total mass is going to be 115. Spinning in the stool, initial angular velocity is going to be 1 rotation per minute, approximately 6.24 radians per second. And they're going to hold the weights at their fully extended wingspan, which gives them a diameter, hand to hand, of 150 centimeters. They're then going to pull their limbs in. We're going to figure out what their speed increases to. And for simplicity's sake, we are assuming that this human is just a cylinder. So this works like a collision. Total momentum initial equals total momentum final. It's just the rotational type instead of the linear type. The initial angular momentum is going to be the initial moment of inertia times the initial angular speed. Final angular momentum will be final moment of inertia times, that's not squared, final angular speed. Assuming a human is a cylinder for simplicity's sake, That formula is 1/2 mass times radius squared. So that is what we will use for I. Note that the radius changes from start to finish, but mass doesn't. So when I input, so when I sub in the moment of inertia formula, I'm doing 1/2 and just m on both sides because it's the same amount of matter. What's changing is the functional radius of the object, or of the person with their limbs pulled in. Now this won't be a perfect representation because, again, humans aren't cylinders, but it'll get the idea across. Any questions getting to this point? Okay. Interesting note before we move on. We can actually do some simplification cancellations here as well. Because we've only really got the one term on both sides, and they both have a 1/2 and the same m in them. So actually, your mass doesn't really matter, only your wingspan. Sorry. Okay, radius 1, this person's initial wingspan is 150 centimeters. There's two problems with that. One, it's not meters. Two, it's diameter, not radius. That's hand to hand. So we gotta cut it in half and turn it into meters. So I'm gonna put 1.5 over 2. Does that make sense? Do note though, the radius is squared, so this fraction is squared. Make sure you do the fraction interior correct first and then square it. And the initial angular speed was 1 rad per second, so 2 pi radians per second, which is 6.24. Wait, 6.28. I've been writing 4 all day, whoops. On the final side, the radius of the diameter shrinks from 1.5 to 0.55. Still got to cut it in half and still got to square it. And then we solve for omega final. Pleasure. Anyone disagree with just shy of 47 rad per second? Of note, that is about 7.5 times faster. Which, again, might not be totally accurate for what I just did because, again, I am not a cylinder. My mass distribution is very different to that. But it certainly felt like I was going 7 times faster. Any questions?
Bless you, Ted.
I am in the habit with my wife of us saying bless you for every single noise. So if I hear something, I just say bless you as a reflex, but that was just something dropping.
Yeah, and I just cracked my back before and you said bless you.
Okay, sorry, it's a weird, I don't think it's weird, but it's a thing I do, so disclaimer, I guess. any errant noise I hear, that is my reader dice. Just like any errant motion I see, I feel like hand raised, question, swirl. Any questions? I think I asked that already. Let me know if you need anything. That's the last of the new rotation information. So next week we're moving on to something different. And let me know if you need anything. Have a great weekend. You too. Thanks.